In this video, I want to talk about how to graph a rational function that has an oblique asymptote. So we've already talked about rational functions where the degree of the numerator is less than the degree of the denominator. Those ones have a horizontal asymptote at y equals 0. And then we talked about rational functions where the degree of the numerator equals the degree of the denominator. And those had a horizontal asymptote where you divided the leading coefficients of the numerator and the denominator. Now, but we didn't talk about where the degree of the numerator is greater than the degree of the denominator. So in those cases, like in this one, we can have what's called an oblique asymptote. In particular, we have an oblique asymptote when the degree of the numerator is equal to the degree of the denominator plus 1. So that is when the degree of the numerator is 1 more in degree than the denominator. So the other thing, though, that we have to check for is we have to make sure that they can't be simplified at all. So we want to first look at this and see, can this be simplified or factored at all? I think in this case the answer is no, but sometimes it's the case that it can be factored and that you can kind of cancel out the top and the bottom, and in that case we have a different scenario, which we'll talk about in a different video. But in this case we're talking about when the degree of the denominator is greater than the degree of the numerator is greater than the degree of the denominator, and it's greater by 1, and it can't be simplified, then we have what's called an oblique asymptote. So the way that we find an oblique asymptote is by using polynomial long division. So we do x squared plus x plus 2 divided by x plus 1. And so we see how many times is x go into x squared, it's x. And then we multiply back x squared plus x. And then this is all going to be 0. Bring down the 2, so 2 is going to be our remainder here. And this just happened to be an extra simple one. So we don't worry about the remainder, but it's just y equals x. So in general, it's going to be an equation of the form y equals mx plus b. Ours just happened to be extra simple because this is kind of a simple equation, but it's not always going to be that simple, but it will always be of the form y equals mx plus b. So let's go ahead and graph that. Let's look at, so y equals x is just a slope, or a line that goes through 0, and the rise is 1, and the run is 1. So, okay, this looks pretty good. So I'm going to graph a dotted line here. Okay. And that is my oblique asymptote. Now, we can still have vertical asymptotes. So remember that vertical asymptotes happen whenever the denominator is equal to 0. So in this case, our vertical asymptote is going to be x equals -1. So let's go ahead and draw that in. So x equals -1 is our vertical asymptote. And now let's try to graph this. Now, whenever you have two asymptotes like this, the graph might either go in the smaller, the sort of acute angled spaces, or it might go in the obtuse angled spaces, but it'll kind of be the mirror image more or less. But let's just go ahead and plot some points and just see what it's going to be. So I see that if x equals 0, all of these x parts are going to go away, so it's just going to be 2. So if x equals 0, y equals 2. So that's an easy point to plot. Let's see about when x equals 1. When x equals 1, we have 1 plus 1 plus 2 over, so 1 plus 1 plus 2 is 4, over 1 plus 1 is 2. So that's going to be 2 also. So that looks kind of silly, but what's happening, I think, is in between these 2 points, there's a curve here that goes like that. But let's go ahead and plot what happens when x equals 2. So that would be 2 squared plus 2 plus 2 over 2 plus 1. So this would be, let's see, 4 plus 4 is 8 over 3. So 8 over 3 is not quite 3. So it's something like this. Somewhere around there. So, and if you plotted a half, it would be somewhere up here because we're going to be going closer and closer toward that vertical asymptote. And then we're coming down and we're getting closer and closer to this asymptote as well. Let me see if I can do a better job of that. So it's going to look something like this. Let me try one more time to get a smoother picture here. There we go. Okay, so it's going to look something like that. It's moving toward both of the asymptotes and then going through those points that we found. All right, so let's try to graph the other piece of it, which we know now should be located in here somewhere. So let's try to figure out what -2 is going to be. So that's going to be -2 squared minus 2 plus 2 over -2 plus 1. So this is 4 minus 2 plus 2 is just 4 over -1, so -4. Oops, that was off the screen. All right, so -4. So -2 is at -4, which is right here. Let's go ahead and graph -3. So for -3, we have -3 squared minus 3 plus 2 over -3 plus 1. So that's 9 minus 3 plus 2 over -2. And that is 6 plus 2 is 8. Is that right? Yeah, 6 plus 2 is 8 over -2 is -4. So that should be over here. And it looks like the same kind of thing is happening here where we're going to curve around like this. But let's go ahead and plug in -4 also. So if we plug in -4, we'll have -4 squared minus 4 plus 2 over -4 plus 1, which should be 16 minus 4 plus 2 over -3. So this is 12 plus 2 is 14 over -3, which is going to be close to, but not quite, -5. So this will be like right there. Okay, so same kind of thing is happening over here. We're getting closer and closer to this asymptote. We're coming around and we're getting closer and closer to that asymptote. And so that is how you graph a rational function with an oblique asymptote. Remember that the degree of the numerator needs to be equal to the degree of the denominator plus 1. Also remember that you need to try to simplify this first. And if it can simplify, it's a different kind of thing. We're going to talk about that different kind of thing in another video. But for now, this is how to graph a rational function with an oblique asymptote.